This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The first lecture series, the Bloch equations and image contrast, is broken down into 4 parts. Lecture-01B covers radiofrequency, B1 pulses, and the rotating frame. The learning objectives for this lecture include being able to explain the principal function of the RF B1 field, including describe the magnitude, spatial, and temporal characteristics of the B1 field, and define the B1 with a mathematical expression. To distinguish between spin, precession, and nutation, to differentiate between the lab and rotating frames, to remember an expression for a circular polarized RF field, and to contrast the equation of motion in the lab and rotating frames. So let's begin by talking about radiofrequency or B1 fields. And shown in the background here is actually a B1 coil that's used as the exciter, and then a diagram of how these birdcage coils function. So here again, we look at a hardware teardown of a typical MRI scanner system. And the component we're interested in discussing right now is this one right here called the body transmit receive coil, or sometimes just called the body coil. And it's responsible for generating the B1 coil. And it shouldn't be confused with another term, which is sometimes also referred to as a body coil, which is a receiver body coil placed close to the body, much as a head coil or a knee coil or a wrist coil. We sometimes refer to a body coil. But in this specific context, we're talking about the body coil most generally as the transmit coil for generating B1 pulses for excitation. So let's think about what the RF or the B1 field characteristics are. The B1 field is a radiofrequency field, so it's in the megahertz range typically. And so this might be 48.57 megahertz per Tesla in the case of hydrogen nuclei. And once we've determined the externally applied B0 field, then we have a specific operational frequency. And at 1.5 Tesla, this would be nominally 63 megahertz. RF pulses are short in duration, so they're typically hundreds of microseconds, maybe tens of microseconds for the shortest pulses, more typically hundreds of microseconds or milliseconds, and not typically longer than tens of milliseconds. So relatively short in duration. They're small in amplitude, so it's important to appreciate the amplitude of these pulses are only on the order of a few microtesla, so substantially lower than the externally applied B0 field. And they're fundamentally shaped by an envelope function. And we see this on the right-hand side. So the envelope function is some outer function that governs the amplitude of the otherwise time-varying radiofrequency carrier frequency. So this white oscillation here is a 64 megahertz oscillation, and that can be shaped by an envelope function. These fields are circularly polarized. This is a concept that we'll develop a little bit further in this lecture, which means the field itself rotates at the Larmor frequency so that it efficiently can tip the spins with low energy. And these are fundamentally electromagnetic fields, of course. Mathematically, these are perpendicular to the B0 field, and so we'll see why that's important later, but it does fundamentally help us appreciate why such low magnetic field strengths, a few microtesla, are able to tip tip the spin system in the presence of the otherwise very strong external B0 field. The principal use, of course, is for excitation, generating detectable spin, and also for things like refocusing concepts that we'll develop later. The application of RF pulses, of course, makes available the spin system for detection, but it also helps us alternate the image contrast using things like inversion pulses and saturation pulses, or perhaps for signal spoiling as well. I want to make a distinction between 3 different terms that may colloquially sound similar, but in fact are quite distinct in the context of MR. So the hydrogen nucleus itself has intrinsic spin. This is a physical property of the hydrogen nucleus that we can't create nor destroy, just like spin, just like mass and charge, rather. We also have this concept of precession, which we developed in the previous lecture, which tells us that the spin system will precess at omega 0 depending on the gyromagnetic ratio and the externally applied B0 field. And this is the bulk precessional behavior that we're generally familiar with. In a very similar way, although at much lower magnetic field amplitudes, the RF pulses, which are generated by B1 fields, will contribute to so-called nutation or tipping of the spins. And we'll see this in the diagram on the right in just a second. And they also do so at a particular frequency, which accords with the same gyromagnetic ratio and the amplitude of the applied B1 field. And so here on this diagram on the right-hand side, we can appreciate that inherently there's some spin for the system itself. There's some precession as well at the Larmor frequency, but there's also nutation at a much lower frequency. And so here we can see the combinations of precession and nutation. And nutation is also sometimes referred to as tipping. So we're tipping the bulk magnetization, here shown in the laboratory frame. So an RF pulse imparts so-called forced precession. And I want to make the distinction between free and forced precession. Free precession is what the spin system does simply in the presence of the B0 field. And when we then activate the B1 field, we can force the spin system away from its equilibrium position. And so B0 causes precession about the z-axis, and B1 causes forced precession or nutation. So here's just another example showing when we turn on the B1 exciting field, which I showed the hardware component of in a few slides back. We can see how the spin system itself will be tipped into the transverse plane and excite the magnetization. So we can play this again. You'll see the activation of the B1 coil tipping the precessional magnetization so that it becomes detectable in the so-called transverse plane. And this may be an example of the spins that lie within a slice of an individual subject placed in the scanner. So the RF pulses help us generate so-called transverse magnetization. This is a basic RF pulse, and in fact, this is a linearly polarized RF pulse. So here we can see that the B1 field is a function of time, is shaped by an envelope function, and it's oscillating at the Larmor frequency. So this Larmor frequency is tuned, for example, to match omega 0, which is the frequency that we expect the spin system to be precessing at based on the B0 field. We can manipulate the phase so that we can tip the magnetization in with slightly different phases as well. Now this linearly polarized field, it's called a linearly polarized field because it's oscillating just along a single direction, in this case the I-hat direction. So this is the applied B1 field, this is the pulse envelope function, this is the excitation carrier frequency, and as I said, the initial phase angle. And this is a linearly polarized field. So the resonance condition, which is important to remember, states that the carrier frequency of the RF pulse has to be matched to the Larmor frequency of the spin system. Obviously, if we choose an RF pulse with a very, very different precessional frequency or RF frequency, it wouldn't engage or excite the spins that are exposed to the B0 field and precessing at omega 0. So when we match these two frequencies closely, we engage the resonance phenomena, and this is described here as the resonance condition. So this is the linearly polarized field that we described just a second ago. It's a magnetic field, a B1 field that's oscillating back and forth at the Larmor frequency, shaped by an envelope function, but only pointing along this, in this case, the x direction. And this was really used by first generation MRI systems that used linear polarization. It was simple, it was cheaper, but as we'll see in a moment here, it also has higher RF power. And the RF power, the energy required to generate these fields and ultimately deposited in the subject or object being imaged, is actually quite limiting in many MRI applications. So it's important to identify an approach that will allow for lower RF power, but the same engagement of the spin system. And so here, mathematically, we're just demonstrating that we could have a circularly polarized magnetic field. So in this case, an envelope function that's operating on a cosine of the RF frequency and a sine of the RF frequency. And this particular magnetic field will be a left-hand magnetic field that's rotating at omega RF. At the RF frequency in the transverse plane. And this, we'll see shortly, will generate on-resonance excitation, and it will generate some patient heating. If we add to that a counterclockwise circularly polarized field, which is shown by this mathematical expression here, this is still just a cosine and a sine, but in this case the sign of the sine has changed. We now have a circularly polarized magnetic field. Because this is at a frequency that's the negative of the excitation frequency, it's very, very off resonance. So it doesn't really engage the spin system for excitation, and it only contributes heating to the object. And so what we're showing here mathematically is that the linearly polarized field can be decomposed into two different circularly polarized fields, but only one of these fields is contributing to on-resonance excitation, which does, of course, come with some heating. But this other field is coming with only heating, and it doesn't contribute anything to excitation of the spin system. So we can effectively drop off this counterclockwise circularly polarized system and only use circular polarization. And so modern MRI systems only use this clockwise circular polarization, and they don't engage or excite anything with the counterclockwise system because they really only generate heating for the subject. So this is an interesting development in MR, and even with this, even with circular polarization, many pulse sequences are still SAR limited, that's energy deposition limited for applications at, say, greater than 3 Tesla. So how are the B1 fields generated? Well, typically they're generated using what's called a birdcage coil. This is shown on the right-hand side here. This has a hoop and rung design with some capacitors and resistors as well. This is the most common design. It's highly efficient in terms of energy in and the amount of excitation we get while mitigating heating because we use circular polarization in particular. Nearly all of the fields produced contribute to imaging itself, so that minimizes the heating as well. These are very uniform fields, especially in the radial direction, but it does decay somewhat axially, but it's relatively uniform over a sphere whose length is approximately the diameter of the RF exciting coil itself. And this generates the so-called quadrature field or circularly polarized field. And just some nice examples of what these circularly polarized fields sort of look like are shown on the bottom of this image here. So these are two B1 fields. One is a counterclockwise left-hand field and one is a clockwise right-hand field. And just to orient you, this is the XY or transverse plane, say, of the scanner. And this longer axis here is time. And so we're diagramming the differences between these two. So when I turn on this field here, I can see that as a function of time, this field is generating a counterclockwise excitation in the XY plane. And that engages the spin system and contributes to excitation and some heating. And this field here, let's go back. This field here is precessing, or rather oriented to activate in a clockwise direction, only contributes to heating and does not contribute to spin excitation itself. And so we generally don't use this particular field. So here's a little bit easier to see, the circular polarized description of the B1 field. So again, there's an envelope function, and we'll talk some about envelope functions. That's something that'll be developed outside of this course and a little bit in some later lectures in this course. We see that it's the envelope function operating on both the cosine and minus sine functions. And so here's a typical envelope function that we might use. This is a rect function, and it basically just says that we're turning the RF field on at a certain time. It's precessing at the Larmor frequency to engage the on-resonance condition, and then it's turned off at a particular time. So perhaps the simplest RF pulse that we could think of. And then we've seen some examples of this already, but we can also modulate the RF carrier frequency by a different envelope function, in this case a sync function. And this has certain properties that are useful, for example, in trying to excite thin slices, which we'll see more of when we discuss spatial localization. So a concept I want to develop now or turn to is descriptions of bulk magnetization dynamics in the lab frame versus the rotating frame. And up to this point, we've been considering just the laboratory frame, which is the coordinate frame associated with sort of the room itself in which the MR scanner is anchored. And so here we can see a description of this. Typically the z-axis is oriented, or by definition, along the head-foot direction of the MRI scanner. And we want to define a right-hand coordinate system with x usually in the left-right plane, and then to maintain being a right-handed coordinate system, then we have y pointing down. And so we can see, or we recall rather, that the rotational angular velocity can actually be a vector. It depends on the main magnetic field that the spin system is being exposed to. And so this becomes one description of the Larmor expression anchored to the laboratory coordinate frame. Now, the rotating frame, which I want to introduce now, helps simplify the mathematics and provide more intuitive understanding of spin dynamics. And so in this movie that we're showing here on the right-hand side, we can see that during excitation, the spin is both precessing and nutating. It's nutating to be tipped down to point along the so-called x prime axis. And we use x prime, y prime, z prime to represent the laboratory coordinate frame. In the rotating coordinate frame, something that we'll develop here shortly, the observation and your intuition for what's happening to the spin system becomes a little bit more simple, and in fact the mathematics becomes simpler as well. And in this case, we're demodulating out the radiofrequency precessional behavior, or the Larmor precessional behavior, and just seeing the effects of the RF pulse itself. And to conceptually think about what the rotating frame really represents, it's as if we're spinning at the Larmor frequency and observing the spin system from that perspective. And again, that makes some of the mathematics simpler, which leads to more intuitive understanding of what's going on. But it is important to recognize that both coordinate frames share the same z-axis. And so it's really just a transformation in this xy plane that becomes the difference. And so let's think about this a little bit further. If the rotational frequency of the rotating frame is matched to the bulk magnetization's precessional frequency, then rotational motion of the bulk magnetization is effectively removed or demodulated. And so we can get away from the complexities of precessional behavior by adopting the rotating frame. And the rotating frame's transverse xy plane simply rotates clockwise, or left-handed way, at a frequency omega relative to the scanner's x prime y prime plane. And so now we're just going to get into this coordinate frame of the xy coordinates, which are the rotating frame. And the rotating frame will simplify the mathematical description of spin dynamics, or bulk magnetization dynamics, and again afford a more intuitive understanding of what RF pulses are doing, for example. Okay, so this is the equation of motion that we saw previously. It tells us how the bulk magnetization dynamics depend on the presence of the externally applied B0 field. And I won't go through the derivation here, but there is a way of transforming this system of equations into an equation of motion for an ensemble of spins, or spin isochromats, the bulk magnetization, in the so-called rotating frame. And fundamentally, what we've really introduced here is this demodulating term here, which is the precessional frequency of the spin system divided by the gyromagnetic ratio. And we can make a simple substitution here to describe what's called B effective. So the effective B field that the bulk magnetization experiences in the rotating frame. This is not the actual B field, this is the so-called effective B field. And it's a useful tool for describing what's happening in this rotating frame. And it's a combination of this, what we call a fictitious field that demodulates the apparent effective B0. And this is just taken as the omega rotational frequency divided by the gyromagnetic ratio. And then the actual applied B field, but described in the rotating frame. So we have to transform the physically applied field into the coordinate system of the rotating frame. And then this term will demodulate the precessional behavior. And so if we use this substitution, we end up with an equation of motion that's very, very similar to that used in the laboratory frame. And we'll use this expression from here on out. So to describe the rotational behavior of the bulk magnetization as a function of time. So here, let's consider free precession in the rotating frame and without relaxation. So free precession is just what the spin system does in the presence of the B0 field. We want to work in the rotating frame, and we want to dismiss at this point any considerations for relaxation. So what's the B effective in this case? The B effective is the omega rotation divided by gamma, which in this case is just minus gamma B0 k hat prime, plus the externally applied B0 field described in the right coordinate system. And so we can see mathematically that the addition of these two terms just gives us that the B effective is 0. And this is sort of the value, if you will, of working in the rotational frame, that if we only have the presence of the externally applied B0 field, there is essentially no effective B field apparent in the rotating frame. And so now we can take the effective B field, we can use that in the rotating frame description of the equation of motion. And we can see that when we map out the cross product operator here, we of course have no apparent B field being applied. This gives us a very simple system of differential equations describing the magnetization dynamics, the bulk magnetization dynamics in the rotating frame. And fundamentally, if we solve this system of differential equations, we find that we just get constant components in the rotating frame in the absence of relaxation. So any component of magnetization just retains its initial state as a consequence of free precession in the rotating frame in the absence of relaxation. And so now we might wonder, how do RF pulses actually tip the magnetization and result in excitation? And for that, we'll have to return to one of the following lectures. Thanks for joining us, and click below for subsequent lectures.